In this lecture, we will continue with the analysis of shear stress or shear flow in skin stringer idealized beam. So, in the last lecture, we have figured out how to find out the shear center of and the shear flow in an open cross-section beam, which is idealized using the skin stringer simplification. So in this lecture, we will try to see how to handle a portion of an aircraft component which is curved, which is not horizontal or vertical or inclined in a linear fashion. Okay, so you should be able to appreciate that this kind of curve component is going to be very common in any of the aircraft structure, be it wing, a fuselage, or any tail or aerodynamic surfaces. Now, let us see how are we going to figure out what is going to be the shear flow in this kind of uh, skin stringer idealized but carved portion of a beam. So the portion that is shown here could be a portion of open cross section beam or a closed cross section beam, which is not going to matter much here. So the two black dots showed at point 1 and 2 are the booms. So let me call them this as boom 1 and this as boom 2. Okay, and Q12 is the shear flow at any arbitrary point on the portion between 1 and 2. Now, if Q12 is the shear flow and ds is the coordinate in the tangential direction, this ds, sorry, this should not be ds, I should call this as rather the s direction. Okay, so let me even erase this off. Okay, so if I take a small portion ds here, okay, and that I can write in terms of dx and dy. So this is going to be dx, this is going to be dy, and this is going to be ds. Okay, so s being the tangential component and q2 is of course in the direction of s. Now let me also call this angle that the s coordinate makes with the x-axis as phi. Okay, and sx and sy are the applied shear forces. Okay, so let us try to balance sx. So if I try to balance sx in terms of the shear flow q12, then sx is going to be q12 into ds, which is the force in s direction. So this is the force in s direction, okay, into cos phi, phi being the angle between s and x. So ds into cos phi is nothing but q12 into dx, and the limit of the integral is going to be from x1 to x2, where x1, y1 are the coordinates of point 1 and x2, y2 are the coordinates of point 2. Okay, so this is going to be therefore equal to q12 into x2 minus x1, as q12 is constant, right, as we have discussed in detail in the last lecture. So it is going to be constant in between 1 and 2, boom 1 and boom 2, or B1 and B2, right? So I get Sx therefore is equal to Q1 to X2 minus X1. So similarly, I can say that Sy, if I do the same kind of formulation, it is going to end up being Q1 to Y2 minus Y1. Okay. So now if we look into the resultant of the shear stress, so the resultant of the shear stress, sorry, not shear stress, of course, the shear force. The resultant of the shear force is S, which is the, and therefore it is going to be into Q12. Okay, so this is how it is going to look like. So now what about this? What about this one? This is nothing but the length L, that is the straight line distance between 1 and 2. So this distance is L, which is nothing but x2 minus x1 square plus y2 minus y1 square. So therefore, the neat result that I get out of this is S, which is the resultant, is going to be Q, is going to be Q12 into L. Okay, so therefore, if I know the resultant of the shear forces, then the Q12 or the shear flow that will develop in the curved portion between two boom is going to be S by L. Okay, so this is an important corollary that we should keep in mind, and this will be very handy when we are trying to analyze or solve uh, the problem of a aircraft component with a skin stringer idealization. Okay, so let me call it at equation 1. Okay, now let us see how to find out the shear center of a curved component of an aircraft. So I can very well clear this canvas and let me see Okay, so I have drawn this figure which shows a curved component of a skin stringer idealized beam, okay, with two booms B1 and B2 at the 2 points, at the two endpoints 1 and 2. The S, capital S, shown in red color is the resultant shear force. And this resultant shear force that is acting on this portion 1, 2 is going to produce a shear flow Q1, 2, which is going to be in the tangential direction. So now my job is to find out the shear center for this curve position. So that's what we are going to do, to try to find out the shear center of this curve position. So let us take any arbitrary point O and zeta be the perpendicular distance of S from the parallel line passing through O. Okay, so zeta is what we need to find. So zeta is what we need to find. Now, what I have to do to find out the shear center is to take the moment about O. So, O is an arbitrarily chosen point. So, it depends on the engineer who is working on it. So, any convenient point that minimizes the calculation is what O is. Okay. So, taking moment about O, what we get, the moment because of the applied force is S into zeta. And that, because that should be equated to the moment about O due to the shear flow, which is going to be Q12 into ds, that is the force, into PS. PS is the perpendicular distance of ds from point O. So this is the force part and this is the moment arm about O. Oh, and so of course this is going, and then of course we have to integrate since we are taking it over an elemental length ds. Okay, so therefore S into zeta is going to be Q12, which is constant, into PS into ds. So if you remember, sometime back in one of the lecture I said that PS into ds is nothing but twice, the integral of PS into ds is nothing but twice into the area enclosed by S about the point O. Okay, so this is going to be nothing but Q12 into twice the area. Which area? The area enclosed by the total curved line. So let me just try to draw this area. So this area is what I'm talking about. Okay, so right from your geometry, you know this is the shaded, green shaded portion is the area A that we are talking about. Right? So PS being the perpendicular distance, and if we take the integration over ds, then it is going to give us twice the area. So this is going to be 2Q12 into 2A. Now let us go one step further and say that Q12 we know is going to be S by L into 2A, right? We have derived earlier that the resultant shear force is going to be Q12 into the straight line distance between point 1 and 2. Okay, so therefore the shear center zeta is going to be just 2A by L for a skin stringer idealized curve portion. Right? So L is the longitudinal, sorry, the straight line distance between point 1 and 2, and L is the straight line distance between point 1 and 2, and A is the area covered by point 1 and 2 about the point O. Okay, so this gives us a very neat expression to this as well. The first equation gives us two very neat equations that will become very handy when we are trying to find out the shear flow or shear stress distribution in a skin stringer idealized aircraft component. Okay, so with this we are going to move into another example where we will translate from open cross section B to closed cross section B. Okay, so let me move into a new topic, which is shear flow or stress. Let me get rid of this shear stress part. Let me just call it shear flow. So shear flow in closed cross section skin stringer idealized beam. Okay, so it is best to explain the technique by using an example. So I am going to use a generic example and try to explain the process of finding out the shear flow in a closed cross section skin stringer idealized beam. So I'm going to take some time in drawing the beam cross section. So all the lines are straight line, though they may not look like one, but these are all straight lines. Right, so there is boom at each of the junction. So at each junction there is a boom. Okay, so this is the x-axis. So the section is symmetric about x-axis. I haven't drawn it so, but the section is symmetric about x-axis. Okay, so let me draw the dimensions. So this is, all dimensions are in mm. So this is 60. This is 100. This is 200. Okay, so this is 120. This is 240. Yeah, so this is 240 and this is also 240. So let me number the booms. So we are going to start from 1 here. So this is 1, 2, 3, 4, 5, 6, 7, and 8. Okay, the areas of the booms are going to be, this is 400 millimeter square, this is 250 millimeter square, this is 200, and it is symmetric, so 200, 250, 400, 100, and 100. Okay, so we say that, so the question is, find the shear flow for Sy equals to 10 kilonewton applied through the shear center. Okay, so we need to find out the shear flow because of Sy, which is 10 kilonewton, being applied at the shear center. Okay, now since this cross section is symmetric, Ixy is going to be 0 and Sx is also equal to 0. Okay, so because of these two reasons, we know that my QR minus 1 is going to be minus Sy by Ixx into BR into YR. Okay, so this is the equation that I'm going to deal with. Okay, let me call it as equation 1. So the only sectional property that I'm going to need is Ixx. So let me try to find out Ixx. Okay, I need the figure. So if I try to find out Ixx, since it is symmetric, so I will put a 2 here because there is always a symmetric boom, okay, on the other side of x-axis. So let me calculate it. So it twice, so let me, for 4 and 5, it is 100 into 50 square. For 3 and 6, it is 400 into 100 square, plus for 2 and 7, it is 250 into 100 square, plus 200 into 30 square. Okay, that is my Ixx. I mean, you should appreciate the ease that you have with skin stringer idealized cross section in all the aspects, and even in finding out the sectional property. So this is 13.86 into 10 to the power 6 millimeter 4. Okay, now let us go ahead and find, so this is one piece of information that I will keep needing. Okay, so let us go ahead and find out the shear flow in each of the portion of the cross section. So before I do that, let me just erase, clean this part, because I would need to refer to this figure all the time. So if I erase this, also don't need this. You can also keep this in mind. Okay, I just need Ixx. Okay, so I will write down Ixx here. So Ixx is 13.86 into 10 to the power 6 millimeter 4. Okay, so now let us assume or let us consider, not assume, let us consider that Q23 is Q0. Okay, so Q23 is Q0, right? And therefore, if I start from here, so I can say that for what is going to be Q34? Q34 is minus 10 into 10 to the power 3, that is SY, so this is SY, okay, by 13.86 into 10 to the power 6, which is my IXX, into BR is basically 400, which is my B3, okay, into YR is going to be 100, okay, which is Y3, okay, plus Q0. Q0 is always there, which is not known. So this is similar to solving the shear flow problem for a closed cross-section beam, which has not been idealized, the actual closed cross-section beam. There also we take a cut and we take a point, and where we say that the shear flow there is Q0. Okay, but the good part here is that shear flow is constant in any portion of the idealized beam between two booms. So Q0 is equal to Q23. So I mean Q0 is the value of the shear flow in this entire position 2, 3. Okay, so now therefore this, if I simplify, is going to be minus 28.9 Newton per millimeter plus Q0. Okay, so similarly I can see what is going to be Q45. Okay, Q45 is minus 10 into 10 to the power 3 by 13.86 into 10 to the power 6 into 100 into 50, okay, plus Q34, okay, which is going to be minus 5 into 10 to the power 7 by 13.86, okay, which will turn out to be minus 32.5 plus Q0. Okay, now let us go to find out Q56. So Q56 is going to be minus 10 into minus 50, because y of 5 is going to be minus 50 plus Q45, which is going to be, if you calculate, it is going to be minus 28.9 plus Q0, which is actually equal to Q34, and that is correct due to symmetry. Okay, which is correct because there is a symmetry. Okay, so similarly I can find out Q67, which is and that if you look into it, it is going to be Q0, which is equal to Q23 due to symmetry. I actually didn't need to find out the entire, for the entire cross section. I could have easily used the symmetry. Okay, now let me go further ahead and find out Q78, which I don't know yet. So minus 10. And that, if you calculate, is going to be 18.1 plus Q0. Okay, then Q81 is going to be okay. So then Q12 again, sorry, Q12 is going to be 18.1 plus Q0 from symmetry. You can either find it out or you can directly say from symmetry it is going to look like this. Okay, now I have got all the values for the shear flow. So let me just draw this and see what we are going to do next. So let me just draw all the shear flow. So this is going to be Q0, and this is going to be minus 28.9. So this is 28.9 minus Q0, and this is going to be minus 32.5 minus Q0, and then I have again minus 28.9. So this is going to be minus 28.9, sorry, plus minus Q0. Okay, and then I have, so and then I'm going to have what is for Q67. Q67 is Q0 in this direction. Sorry, Q0 is going to be in this direction. So this is going to be Q0, and then this is going to be 18.1 plus Q0. This is going to be, how much did I get? 22.4 plus Q0, and this is 18.1 plus Q0. Okay, so this is the shear flow distribution as of now, where my Q0 is unknown. Okay, so let me now try to find out Q0. Okay, so if I try to find out Q0 using Bread-Bether's theorem, I can say that tau ds is going to be equal to 0, and therefore this is going to lead to Q0 2 into 240, because Q0 is for every portion, is there for every portion of the cross section. 60 plus 100 plus 2 into 120 square plus 50 square plus 2 into So this is the Q0 part, and then I have, so this can actually be written as QDS equals to 0. Okay, so plus I have, so minus, because minus 28.9 into 2 into the length, that is 120 square plus 50 square, minus 32.5 into 100 plus 22.4 into 60 plus 2 into 18.1 into 70 square plus 240 square, and that should be equated to 0. So that is going to give me, if I calculate this, then 1400 Q0 minus, I have skipped some steps between, so it is going to be 7514 minus 3250 plus 1344 plus 9050, and that is equal to 0. So if you solve for this, Q0 is going to be 0.264 Newton per millimeter. Okay, so that is what it is going to look like. Okay, so that is going to give you the solution. So once I know Q0, I have to just substitute in the above equation and get all the shear flows. Okay, and since Q0 is a very small number, the signs of the shear flow is not going to change much, and so the signs that we have drawn, okay, since Q0 is only 0.264, it's, the signs are not going to change much, and this is how it is going to look like. The shear flow is going to look exactly the way we have done. So with this, I will end this lecture. In next lecture, we will try to solve more of a, we will try to solve a beam cross section which will look more like an aircraft component. Thank you.